And I was just working on a solution here, so I'm going to comment this out. Let's see here.
Hey, Paul.
What's up?
For the purposes of viewing this on YouTube later, would you be able to bump the font sizes on your terminal?
Yeah, let me blow that up right now. Yeah, 4K screens don't work well for YouTube videos. This one's probably big enough, but this one is where we really need the extra help. Okay, cool. Is that better?
Yeah, man.
Okay, cool. So I'm going to comment out the solution just to show you how everything works. So the problem that happened last week is that when I was setting up the test, we didn't have all of the philosophers sharing a fork. So I'm just going to briefly go over what the Dining Philosophers is one more time. So we have 5 philosophers sitting around a table, and between each of them is one fork. These weird philosophers like to share forks for some reason. They don't want to have their own forks, and they have to have 2 forks to eat. So you have 5 people, 5 forks. You don't have enough forks for everyone to eat simultaneously. You need to have 10 forks. So we only have 5. So at most we can have 2 philosophers eating at a time, because that requires 4 forks, and then you have like 1 left over. So when we first did this, we were going over mutexes and how you can kind of cause a staggering effect by having one philosopher start eating with a different fork. If one of them starts eating with the right fork and all of the other ones start with their left fork, then you have this kind of it kind of propagates which one is allowed to eat, and it works nicely, but it only allows one of them to eat at a time. So in the test setup, I didn't have the last philosopher share the fork with the first philosopher, which is what you're supposed to do when you have a circle. So that's why it didn't work correctly. So just to show you what's been done to fix that test, let's see here. So we just say if you're the last philosopher, then share with the first philosopher's left. Your right is the last philosopher's, or the first philosopher's left. So yeah, this fixes the test setup, and then you can see the deadlock. So what I'm going to do at the bottom of the screen is I'm going to run the test with using the same way we would do it with a simple mutex. We're using channels as mutexes here. I'm going to do the same thing, and we're going to see it hopefully deadlock. So it's running, each philosopher is running about 3 seconds when they eat. And I think we have a deadlock here. So we can see that someone picked up the right fork. 4240. So these are the pointer addresses for each fork. So each fork is a channel. A channel is a reference type in Go. And we're looking at the address to keep an eye, to know which exact fork we're dealing with here. So we see here that one picked up 4240. So the other person at the table who would pick up that same fork would be number 1's right is 2's left. So if we look at 2, let's see here, 2 picked up right. Did 2 pick up left? Yeah, there's 2, there's 1. I think what's happening here is that this one is not able to pick up the fork because 2 already has it. I actually have the log printed out before it. So we have a deadlock condition. I'm going to go over the test and why it's failing, and we'll fluff it up a bit, get it nice and working well. So the first thing I'm going to do is show you how the channel works as a mutex. We went over this last week, so this is a bit of a rehash. So hopefully this isn't too redundant. So in Go, a channel is it's like a queue. You put something in and it gets taken out from the other end. And you can have a queue that's of 0 size. So when you have a queue of 0 size, that means when you put something in, there has to be someone else pulling something out. So what we do is we create a queue of size 1 so that we can fit one thing inside of it. And we use that as a way of marking that we have control of an access of a resource. So normally we use mutexes to do this, where we lock and unlock a critical zone. But you can do the same thing with the channel. The nice thing about channels is that you can actually choose to wait on one thing or another. You can have multiple events that you're waiting for.
Can I ask a quick question?
Go for it.
So like with the channel, you've got the pushing, we've got one side that's pushing an item into the queue, and then the other side's pulling an item off the queue. Do those two sides have to synchronize as you're like adding and removing? Meaning,
Yeah,
like,
so
okay, and that's why we're applying the mutex to effectively say that this queue is locked. I'm going to put an item on, or I'm going to pull an item off between
no,
the two.
you don't need a mutex to do that. So the way that the channels work is that they're thread safe and they're
Okay.
designed for synchronizing two go routines. So you got two go routines, and then there's a point in the go routine where they're both trying to communicate on the same channel. They sync up, even though they're at different phases of their execution. One will just be blocked until the other one gets to
Okay.
the point to where
And
they can then pass that value.
that's the beauty of it, right? Because then you don't have to manage that synchronization yourself in the code, which is hard to do, right?
Exactly.
Okay.
Yeah.
Okay.
Yeah, so it's kind of, it seems a little counterintuitive, because when you think of concurrency and parallelism, you're like, I want these to run independent of each other.
Yeah.
But every once in a while, you need to have a synchronization event where they both stop and lock at some position and exchange information and then proceed independently. So the way we get around that, though, because right now the way we're using it to cheat and use it as a mutex, we have to make it a size of 1. If you make something a size of 1, then that means that you don't have to wait for someone to pull on the other end. You can put something in there and it'll sit there like a mailbox and wait till eventually someone pulls it out.
It's like an IO
So
select, or the select system call. It'll like sit there and block until something's ready to be read.
it won't block the person who put something in there. So the go routine that
But
puts a
the
value into it, but the other one will wait until something is made
okay.
available. Yeah.
So it's like it's sort of like a way of doing forking without having to fork. You can do it in process. The other end will just sort of sit and wait and listen until there's work to be done, and then
Yeah.
you don't have to deal with the actual synchronization between the two. You create a queue of a size 1. You start the channel. The other side of the channel is like, okay, I know you want me to do work, but there's no work to be done here, so I'm just going to wait until you push something into the queue. Is that right? Am I paraphrasing okay?
I think so. The thing is, so if you have someone that's always listening for work, then you don't really need a queue of size 1. The reason why we have a queue of size 1 in this case is because we don't have another go routine that's pulling that data out. If you try to push data into a channel and there's not something on the other end, you'll deadlock your thread because you're the only one communicating on this channel. So what you can do is you can give it a size, and by giving it a size, you can put something in there and it doesn't have to be someone on the other end. You can actually pull it out yourself. So in that
Oh,
case, it's just like a regular slice or a
okay.
regular queue that has nothing to do with concurrency.
Got it.
Yeah, so it's sometimes people use queues as a way to like handle like pressure from, like, you have a lot of requests coming in and you want them to buffer up in memory because you know you don't have enough, you have a concurrency limit that doesn't allow you to service everyone. You're like, okay, I'll use some of that memory I have available to actually queue these up in memory, and then when I have a worker available to pull it off. So you'll see that sometimes someone will create a queue of like requests and it'll have a maximum that builds up. And then when that maximum is hit, then you'll
You
start
block.
blocking clients that want to
Add more to the
make
queue.
requests. Yeah. So I'll show you how that's actually declared. So in our test setup, the way we do that is we say we want to make a struct, or sorry, a channel of empty structs of size 1. So that 1 right there, that's the critical part. If you just omit it when you have a normal queue. And typically you want to work with a queue of size 0 because that lets you know that everything is working in your program really well. If you put in these buffers that are not needed or they're like auxiliary You know,
Mhm.
they're just kind of there because they're nice to have. That won't make certain concurrency problems obvious in your program. So usually you want to have a queue of size 0 unless it deadlocks you in certain situations like it does in this problem.
Mhm. Okay.
So on the right-hand side here, what's happening is that we create all the philosophers, we create all of their forks. Their forks are all channels. And then what we do here is we signal to the philosophers we want you to start. So just going over again what this is, we have a channel, and that channel is just, it's of size 0 because we're actually not going to put anything in it. What we're going to do is before the workers start, we're going to close that channel. And closing a channel is a way of broadcasting an event to all the listeners. So every thread, or sorry, every philosopher's go routine is waiting for the start event. So when I close it on line 41, that'll signal to all of them to roughly start at about the same time. And that's because there's some latency in the scheduler for getting a go routine started. So we don't want them to be too staggered where one philosopher just does all its work before there's a chance to have contention with the other workers.
That's neat. So you can like allocate the multiple channels first, and then to signal like when to start the race or when to get going, as opposed to having them start running as soon as they're created.
Yeah, because you'll see sometimes if you have like a really fast machine, you might see a bunch of them just like really quickly sprint
Right.
through the problem. And then it's like, okay, this isn't really demonstrating the problem. So
Because the last
get
philosopher will end up being last in terms of getting started.
exactly. So this is kind of like a starter pistol where everyone's lined up and then they start the problem at the same
I
time.
like that analogy.
Yeah, I was thinking of calling it pistol, but I was afraid people might think it was too violent or something. So I'm keeping it just start for right now.
Yep.
So we start the go routine worker. We tell them we want them to run. Actually, I'm ignoring this value. So what I'm going to do right here is I'm going to make a quick fix. So we're telling the worker that we want you to run 5 times, and we're also providing the waiter. And I'll get to the waiter in a little bit. For right now, I just want to demonstrate the problem with the naive approach. So over here, what we're having is each philosopher, and I'll go over what a philosopher is. A philosopher is just an ID number, so we can keep track of them. And then the left and right fork, which are represented by structs or channel structs, empty channel structs. And then when we go to the loop here, the loop that's trying to run every so often. So it's in the bottom, you can see that test finally died. It must have been 10 minutes or something. It died.
Sorry to interrupt. Could I ask a quick question?
Sure,
You
go for it.
said the left and right was the forks. Is it the forks or is it the philosopher sitting next to them?
It's the fork. Well, I mean, it's kind of symbolic of the other side of the philosopher. Like they're sharing a side is essentially it. The fork represents the shared side between the philosophers.
Okay, so there's
So
going to be a missing link between 2 philosophers, which would be the missing fork.
so that's what happened in the last.
Sorry. Okay, I'll catch up.
Yeah. So, oh no, what I mean is in the last time we did this, I didn't have the last person sharing a fork with the first person because they're sitting in a circle.
Right.
Right. So it's a circular array, and that's where the problem came. So
Okay.
everyone will share a fork with the philosopher to their left and to their right. That will always be satisfied now. So yeah, there's a left fork, a right fork, and that is shared with the philosopher next to them. So what we're going to have here is the philosopher is going to try to pick up their left and then pick up their right. Once they have both forks, they're going to eat, and we're going to make them just sleep for 3 seconds to represent work that's being done. And then we're going to say, okay, we're going to increment this counter to say that we had 1 successful eating loop.
You had a bite of your meal. Got it.
Yeah, you ate your meal and now you're ready to think, because we're always transitioning from being hungry to eating to thinking. So the philosopher will put down their left fork and then put down their right fork. and then they'll think right here. And thinking is just transitioning to another state. But as we saw over here, it crapped out. There was a deadlock because two philosophers were going for the same fork. I think it was 1 and 2 that were going for the same fork. And that's not good. So Will, John, were you on last week?
No, I was not.
Okay. Will, you were on last
Left
week.
behind.
No.
Will, do you want to take a stab at what the solution was? Do you want to give it a shot or put you on the spot again
Sorry.
after the Giddily demo?
Yeah, so cruel, Paul.
Before
so-
Will jumps in, is there any chance you could just go over that output just so I can get a better understanding of like how you're seeing the deadlock? Like I see a
Yeah.
panic.
I'm going to add a better log statement.
I hope
While
that gives
do
you some
that,
time,
too.
Will.
Buying you some time there.
I'm just not used to the go output. So I see a panic occurred at about 10 milliseconds. Go routine 21. So that's the identifier of the routine that had the panic, I think.
So the panic is happening because the test timed out.
I see. Okay.
There's this whole test framework, and it has, I think, a default time limit of like 10 minutes. And when it hits that point, then it says your test is taking too long. Just
Okay.
figure it out. We can
because
change that limit to be faster. Oh, go ahead.
I'm sorry, I interrupted. I think I understand. Now the deadlock was because nothing was happening and
Yeah.
the timeout occurred. And the fact that the timeout occurred implies that, hey, they didn't finish eating, which means that somebody's stuck somewhere.
Yeah. So
Okay.
if we didn't have this time out there, it would sit forever. It was
Okay.
it was stuck indefinitely.
Thank you.
Yeah, no problem. So I'm just going to add a little bit better logging here. Let's say reaching for the left, and then we'll have reaching for the right. So that way we can see this. I think this is a little bit easier, even though it's more verbose output in the logs here. It's a little easier to see where it gets stuck if you see like when someone's about to try to acquire that lock versus someone who already has acquired that lock.
I think you need to bump up where that log statement is.
Which one? Oh, you're right.
Line
Yeah.
56 needs to go up to 53.
Whoops. There we go. So for the left, it should be accurate. So we can see here 1 picked up left and 0 is reaching for left. Or sorry. Where is it? No, 0 was able to pick it up. Yeah, we might need that missing log statement. So let me try that again. And do we already find a deadlock? We might have found a deadlock already. So 0 is reaching for right, which is 360 right here. And then, so 0 is sharing the right with left. Left is reaching for 4360. You see that right here. 1 is stuck because it's trying to pick up the right, 360. And then 360, or sorry, 3C0. 3C0.
So that percent
picked
P,
it
when we
up.
go, we're printing sp.right. That's printing the address of right? But right has an ID as well. Would it be easier if we saw the ID of right?
No, it actually doesn't have an ID, not the
Oh,
way I
okay.
designed it. Yeah,
Okay,
I was
sorry.
too lazy. I should have put an ID in there. Next time I'll put like, IDs will be emojis next time, because the emojis are so easy to identify in the log output. If you
Yeah.
just put like a really unique emoji, you can spot it. Like left is picking up heart emoji, or 2 is picking up poop emoji. Like you'll be able to spot it like immediately. So I'll do that next time. Let me
I
put a
love
note
that
in there.
idea.
Yeah, I was doing that with another one of the, I don't know if it was Dining Philosophers or if it was the binary search, but I was putting in a lot of emojis to make it easy. Sometimes you put too many emojis,
And it's
becomes
it's
less
hard to
readable.
decipher. Yeah. But in this case, we have 5 philosophers, so it seems like you could get 5 distinct emoji, and then it makes it fun to see them eating.
Yeah. So we're stuck here, and I want to go over how we can try to resolve this using a more flexible approach. Like right now we have one person picking up the left and one person everyone's picking up the left and then the right. And it becomes problematic because everyone's doing the same thing. They have the same strategy. So what we can do is we can have, well, we can do one of two things. We can have everyone try to pick up different hands opportunistically. Like if only the right is available, then pick up the right. And then if the left isn't available, then put everything down and let someone else eat. So we can try doing that. We can also have a waiter come in and basically control access to the forks and say, okay, you can only have 2 people eating at a time, and try that. So we can try that, and then we can try the ultimate solution that I have here and see how this goes. So there's potential issues here, so we'll see what happens. So I was mentioning that the nice thing about channels is that you can select against them with other channels. And that's really powerful if you want to choose whichever event is available now, instead of having to wait for one item and then check the other item like consecutively in serial, which is a problem. That's just really inefficient. So what we can do here is we can say we're going to try to reach for the left only if we have the waiter's blessing. So the waiter is going to say, we're going to try to put a token into the waiter's plate. And there's only spots for 2 tokens. And so the way we know that is because we created a channel that's of size 2. So once we fill up this, once we fill up the tray, the plate that the waiter's holding, we can't put more stuff on it. So that rate limits us to 2 at a time. So we're going to try to put something onto the waiter's plate. And then once we're able to, we're going to try to do everything. And then we're going to, at the end of this, after we're thinking, then, or actually, I'm sorry, when we're done eating, no, when we're done thinking, we're going to release control of that by taking back our token from the waiter. So let's see if that improves what we're doing. And I should probably add some log statements so we can see that that they're able to proceed. And I have some notes here on how much time this should take. We have a 3-second eating time. We have, we're doing it 5 times 5 philosophers, 3 seconds each. That's 75 seconds. I'm gonna throw this down a little bit actually, because this is too much time. Yeah, we'll keep it at 45. So each one's gonna run 3 times. Okay, so the fastest we can theoretically finish this problem is in 22.5 seconds if we parallelize work with 2 philosophers eating at a time, because each philosopher 5 times, 5 philosophers, 3 seconds each, 45 seconds. So if we want to set a timeout for this test, we can just set it at maybe a little bit over 22.5 to allow for inefficiencies and things we can't control, compile time, that sort of stuff. So we set it at 25 seconds. I think we already passed 25 seconds. We've hit a deadlock. So it's not enough for the waiter to come in and tell the various philosophers which one can come and go, because the waiter is a dumb waiter. The waiter is basically relying on the Go runtime here to randomly, indeterministically assign an empty slot to a philosopher. So we don't have any insight into how that's happening. That's just like a black box to us. We don't know how the Go runtime is making that decision. So the waiter might be seating, it might be allowing 2 philosophers that sit next to each other to go. That's within the realm of possibility. And so when that happens, we have we end up with 2 philosophers that deadlock each other, and then they never get to the bottom here where they can release that that spot on the waiter's plate. So this isn't an this might succeed some of the time. Like if I run this again, and what I'll do to show that this can sometimes work is I'll make a really short work time. Let's do a millisecond, right? And then we'll try it again. And we might be able to get through. It looks like we got a deadlock. Because if we were lucky enough that the waiter always ran the two people opposite of the table from each other, then we would get a success criteria. But it doesn't look like that the odds of that happening are very good. I mean, do we have anyone who knows probability theory who could tell us what are the chances that the two people selected each of the 3 turns or whatever out of 5 people? It doesn't seem like it's that good of odds. Maybe if I ran this test 100 times, we'd see some wins in there.
For science.
What's that?
For science.
Yeah, for science. Yeah, it's not happening. So yeah, we're deadlocked here. The waiter's not intelligent enough. So what we're going to do is we're going to program in a strategy into the philosophers, where the philosophers are going to take advantage of how channels let us opportunistically select the available ready channel and use that to be able to pick the best philosopher. And then if the philosopher is the worst philosopher is chosen, they will give up control, they will concede control so that another philosopher can try. Let's try that. So I'm going to put this back to the value it was before. And then I'm going to show you where this code is done. So here's a select statement. And so the select statement is where we select against the different channels. So we're going to try to select against the left fork, and then we're going to try against the right fork. Or sorry, we're going to try both at the same time. So that's what this statement is saying. It's saying, I want you to try putting a token into the left channel and the right channel. And if you can't put it into either of those, then I want you to run this code, which is just to abort. So if you abort, you're going to return false. So this function right here, try, what it's saying is, I'm going to try, and if I'm successful, it's going to return true. If I try and I'm not successful, it's returning false. So if we were able to successfully pick up the left fork, then we're going to say the other fork that we need to pick up is the right. And we're going to say that before the end of this function, we need to release control of that left fork. And the way this is going to work is that the defer is basically what's it called? It's a first in, first out, or no, yeah, first in, first out queue. So it's a FIFO queue where every time we push a defer in, that defer is going to get popped out immediately. So the last defer statement is the first one to execute. So this is the first one, so it's going to be the last. So first in, last in. I don't remember now. You know what I'm saying.
And so
it's
the
getting
scope of the
in.
defer is within the select statement, is that right?
No, it's within the entire function. So
Okay.
it doesn't run until the function returns.
Got it.
Yeah, so that's actually a common programming mistake too. Like you'll see people put defer statements into for loops, and they expect it to run at the end of the for loop. But then what they'll do, in addition to the problem, there's 2 complications that can happen. First, there's the issue that you think that it'll run at the end of the for loop. But then also you might have a shared variable in your for loop. And that shared variable, if you call defer 5 times and you expect 5 defers to get called, but it's all getting called on the same variable instead of the value that's being assigned to that variable, that becomes a problem. So yeah, there's tricky things when you call defers inside of different kinds of blocks, like select blocks and for loops and stuff. So we're pushing this onto the defer queue. We're pushing this likewise. If we were able to pick up the right instead, we would give up control of the right, and we'd say that the other fork we need to pick up is the left. So then once we've picked up one fork successfully, we try to pick up the other fork. That's the second select statement. Now, if we can't pick up that other fork, we're just going to say, screw it. I don't want to eat anyway, and just let the person next to us try it, which is actually a polite thing to do, right? Like, because normally these philosophers, they're very stubborn and they don't want to share that fork. Once they have the fork, they're like, I have to have the right fork. This philosopher that we're designing here is a much more flexible philosopher, where they are able to say, okay, I don't want everyone to lose, so I'm just going to give up control of that fork. And then just like the other fork, we have to push onto the queue. We have to push on a release of that fork. So we empty that fork out. And if we are able to do all of this, we return true. And now you can see over here, if true, then we're going to eat, right? Actually, there's a little bit of an error here. We should eat before we release the forks. So I'll do that. I'll move this over here. Yes. To be accurate with the other parts of the problem, we want the we want to eat after we've had after we have the 2 forks, but not before we've put them down. So previously it had it so that eating was after the forks have been put down. Okay, so yeah, let's try this out. Oh, and also we have the thing about the waiter. So here what we're doing, we actually don't need a select statement here. So I'll show you why. The select statement's only really needed if you want to have an alternative action, like another channel you're listening on, or a default thing. So we don't need that because, whoops, we don't need that because we're going to do this. Okay. And oh, the other thing is we need to, there's 2 of these. We don't want 2 of these. Oh, sorry. That's from, I'm going to comment this out. So what I'm going to do is we're going to do that. We'll go here. Yeah, that's what we want to do. Okay, so we have the old code commented out, and then we have this new code where we're just waiting for a chance to put something on the waiter's plate. We're going to try. If we're successful, we're going to decrement the count, and then we're going to release control of the waiter by taking our token back from their plate. So let's see how this goes. So we can see people eating, and this should take about 23 seconds if we're successful. People are still eating. We still see log output moving. 24 seconds, pretty close. I'm surprised that we have as much as an extra second there, but I don't know.
What happens if they're not all eating at constant time? Like there's a variable time for each philosopher.
It shouldn't really impact the logic here. We can try doing that too. We can add a random time. So I don't think it'll impact the logic as far as the way the waiter's coordinating them and how they're picking up the forks and stuff. I think what's going to happen is we're just going to what's I guess what obvious to everyone else is that the people who take the longest are going to determine how long this takes, right?
Mm-hmm.
The people who are really fast, they're going to be running in parallel to the slow eaters. So yeah, I don't think that'll be a problem. We can try that though. So I need to remember how to do random.
There was something that you said that's sort of sticking with me, and like where Go has to decide which Go routine to yield execution to. And I'm just wondering, how does it do that? Does it keep track of the time that each Go routine is spending and then take like an average of that and based on that prioritize?
I don't know if it does that. I don't know if
Okay.
it's that fair. That's a
Because
good
if it was
question, though.
balancing, yeah.
That's a good question. That's a good follow. I've seen there's a lot of articles, in-depth articles that people write about the scheduler and how it makes decisions. But I don't think it really cares how fair it is within reason.
Okay.
Maybe it does to a certain extent, but that's a good follow-up question.
The other thing I thought was interesting is like we're giving preference to the left fork right now because we're checking the left fork first to see if it's available, then checking the right fork. Just curious to know what would happen if we were to, instead of giving preference to the left fork, is there any value to just choosing a random fork? Choosing left or right first?
In the select statement,
In the select, yeah.
It's not giving preference to left or right.
Does it
Even
not
though
execute 19 before 24?
that's not defined, I believe, by the Go spec. So if you look at the spec and you read, maybe under the covers, that's what's happening. But as far as how we interpret the spec, the language spec is not saying that the left is preferred over the right. They're all equal candidates. So under the covers, it might be very well doing that. But that's an implementation detail.
Yeah, you don't have to worry about that as the programmer.
Yeah, exactly.
Okay.
So we always just kind of assume that they're of equal standing.
Sometimes random will actually perform better than given the size of the data set. But
yeah, there's some interesting things that the Go maintainers have done to like make people respect the spec.
Yeah.
And like one of the things is the way you iterate over map order, over map key values. So if you iterate over a map, the order that you iterate over the keys is randomized. And
so you can't
like
depend on a deterministic iteration of that map, which is nice.
Because you might think, I've seen it happen before where if I put keys in a certain order, if I iterate over it, they come out that same order. And then people make all these assumptions over the years, and then someone makes a change to the language that was never stated in the spec.
Right, they were dependent on that behavior.
They were dependent on that unspecified behavior, and so that becomes a huge issue. So the same thing with these select statements. If it's not stated in the spec, you shouldn't depend on it because it's at the whims of the Go language maintainers. Like if they change it and they never said you should have been able to depend on it, that's a problem.
Got it.
Yeah.
Those are interesting nuances about the spec. I see why you're talking about the spec more now. And
yeah, that's an important thing to note about Go. I was just listening to a podcast where two of the creators were talking. The early founding creators were talking about how they developed the spec before like anything else. And that was a really important part of the language because some languages, they don't formalize their spec, and then it makes a lot of other things harder to do. But they wrote the spec first, and then they wrote a compiler. Like sometimes you'll have a compiler that's the reference for the design of the language. Yeah, and then they'll write the spec based on that compiler's behavior.
Yeah.
But they did it the other way around. They wrote the spec. And so that their spec is very simple too. Like if you can actually read their spec. Like some languages, it's horrific to like even think about looking at their spec, right? Like I don't even want to know what Java looks like or C++, modern C++. Like there's so many features in there, but Go is so minimal and they've done a good job of keeping it that way that it's fairly friendly to approach. So it's pretty nice. So as far as, no problem. So as far as randomizing this, so what we can do is we can throw in a random integer and then we can just do a modulus on it to make sure that it's within a certain range. Yeah, so we can do, let me pull up the docs on this really quick. That's in Rand, what is that? Math Rand.
Oh, nice. This is the equivalent of RI. See, I love watching this in action.
Okay, so returns as an int from 0 to n. Okay, that's what we want. Panics if n is less than 0. Okay, cool. So we're just going to go over to, where was I? The time. Where's the time?
3.seconds was
Whoops.
that where? No, that's not where they're doing the eating. The eating's line 65, right?
There's two of them. So that's the commented out section. And then we
Oh, pardon me.
have, yeah, so that's the old section that we were going over that doesn't work. And then the
Yeah.
one that does work is on 44. So we'll do rand.int n, and then we want to go from 0 to say, I don't know, 10 or
Maybe
something.
1 to 10, because 0 time is kind of cheating, isn't it?
We could put a +1 on the end.
Yeah.
So, and then we'll do milliseconds instead of seconds just to speed this up. Or how about we do this? We'll do 0 to, we'll do 1 to 2 seconds, just so that it's within the same time range as the first time we ran it.
Yep, it'll be variable between 1 or 2.
Let's see how that goes. So it'll be 1, 2, or 3. And let's actually let's print what this is. So
Yeah, so that 25 seconds will still cover our worst case scenario.
and yeah, actually that's all I want.
Line 47, you'll want to change. Or 40.
Yeah, we'll change that. I'm going to put the print statement for
And
is sleeping seconds. And then we'll put the ID of the philosopher and then the amount of time +1.
You mean eating for X seconds?
Whoops. Well, yeah.
sometimes you sleep while you eat, right?
Yeah. We can do, well, because it's going to sleep after it eats. Yeah, I'm just going to leave it sleeping because we have eating right here on this log statement. So what we're going to do, let's see here.
You want to add the +1 to line 45?
No, well, no, because we want to do n times and then we want to plus it, right? Because it's
Oh,
going
I
to be
see.
0.
So it'll be 0 times.
It'll be 0, 1, or 2 that's returned from the function. And then we want to add 1 more second.
Right. So then don't you want to do n plus 1 times time to second? Otherwise it'll be 0 times.
Yeah, you're right.
Okay.
Yeah. Yeah, that's what we want to do because it'll be 0, 1, 2.
Or 2.
It'll be 1, 2, or 3. Yeah, so that's what we want. N plus 1. And then we'll get rid of this. No, this is what I need. I need the more people that yell at me, the better the code ends up being. So, all right, we got a 47. Where's the error? We got an extra parenthesis. Or
looks like there's an extra paren on the left there.
47 missing comma.
You've got 3 parens on the left.
Oh, yeah. There we go. Okay.
I think that's, and then you still need the paren on the right though, don't you?
Oh, did I move that? Whoops.
Yeah, I think so. There we go. That looks better.
There we go. Okay, so let's try that. Int and time duration. So this is a problem. These are 2 different types.
Oh, my
so,
bad. Sorry, I complicated this.
that's okay.
So
these are 2 distinct different types. I think what I can do is cast this to a duration.
From in 32 to duration. Is that the?
Yeah, so time.second is of type duration. So normally if you put a constant and you multiply it, it knows that you mean of that type. Yeah.
So that's why the 3.time.second was an implicit cast?
Yeah.
Okay, so now are we going to make it under 25 seconds?
So it should be less time, yeah.
12
about half the time. That makes sense. If you have a
But yeah.
random distribution of 1, 2, or 3 seconds.
You're not always going to hit the worst case scenario across all the philosophers.
Yeah.
So I didn't actually, it's the same algorithm, but it accounts for each philosopher eating it for different amounts of time.
Yeah.
That's
And
cool.
the Go runtime did a lot of work for us. Like if we wanted to actually make, the philosophers give up control of the forks or only choose the fork that's available, that's a lot of stuff to write in other
Mhm.
languages, especially
Mhm.
lower level languages. So the concurrency primitives and the language features in Go for concurrency are very high level. Like they allow us to do a lot with very little code. Like Go is usually a pretty low level language, especially to something like Ruby or Python. But when it comes to this sort of stuff, it seems very high level. It lets you get a lot done very safely too. Like if you follow all the idioms correctly.
So the algorithm that we're using here, is there a name for it? Like you said we introduced a waiter, and the waiter is now sort of awarding the fork. Is that right?
So from what I understand, this is just called using the what's the term for it?
It's like a
Going back to my dining.
coordinator.
There's a term for it where we use the actually I'm going to get rid of semaphore here. I want to say they call it like a manager or
Some
a
sort of
coordinator.
coordinator. Yeah. Okay.
Yeah, I think it's a coordinator. So you have a coordinator who manages access to the resource, and that's where the semaphores come in.
Yeah.
So you're essentially rate limiting it, but then we're also making it, we're adding intelligence to the waiter by using the Go runtime with those select statements. So like the waiter is dumb enough to tell two people sitting next to each other to proceed. So we compensate for that with the select statements where we say, okay, if I don't have access to this resource, just give up and let someone else try. So yeah, we make the philosophers less greedy to make up for the lack of intelligence in the waiter. So we could have gone another way with that, and we could have made the waiter smart enough to never pick two philosophers that are sitting next to each other. But then we wouldn't get to play with all the channels and stuff, the fun concurrency stuff. It would have been like more code that's not as fun to write, essentially. So yeah, that's I think that's what it's called, is like a coordinator. This is the same page I was just looking at. I'm trying to find here it is, the Ron Swansons. This is the best illustration. So if we go to semaphores, yeah, so here's they introduced the waiter, right? Do the other ones? Yeah, this is the first one where they do that. So the waiter's the waiter analogy is that they rate limit, right? And they get to pick who goes. So yeah, if you're talking dining philosopher terminology, it'll be called the waiter, or if you're looking for more generic terminology, I think a coordinator is the right way to refer to it. Any other questions?
This is awesome.
I'm glad you liked it.
Thanks for taking all my questions.
Yeah, no worries. The more talking, the better. Like when it's just me like stumbling, then it's not as fun. So the more everyone jumps in, the better. So we were talking last week about going over some more sync primitives. And I just remembered that another time we were doing this, we were talking about error handling. So I was thinking maybe a nice thing to do next time would be to handle errors with concurrency. There's some cool stuff that is in the Go X repos. The X repos are like kind of like auxiliary repos that are secondary to the standard library. There's some cool stuff in there for handling errors concurrently, and there's some stuff we can do with the standard library too. And then there's proper error handling, because there's recently in Go 1.13, they've introduced the idea of error wrapping, where you can wrap an error with another error to add context.
Oh, you can bubble it up.
Yeah. So we can also discuss best practices while showing the concurrency stuff. So I'm going to try to come up with something. I don't know if I'll be able to do it this next week, but maybe the following week. We'll look at doing error handling with concurrency, and maybe I can work it into the Dining Philosophers. I don't know if these remaining problems can take advantage of errors, but we can look at it and maybe try to work it into the same theme so we have like a steady progression. Anybody have any feedback on that?
I like the idea.
Yeah, sounds great.
Okay, cool. All right, we're at 53 minutes here, so I'm gonna call it here. I'll upload this to YouTube. I'm not even gonna upload the last one because I messed up so bad, so sorry about that, Will.
I forgive you.
It's the same material in this one, so I figured we'll just do this one. So I will upload this to YouTube and I'll share in the Go channel. Thank you everyone for participating, and hope to see y'all next time.
Thank you,
Paul.
sir.
Yeah,
Thanks,
thanks
Paul.
for putting this together. This was great. See you next week.
Yeah, no problem. Have a good weekend.
You too.